In section 10.2, we learn how to use second derivatives to help us graph. In order to do that, we need a couple of definitions. The first definition is concave up, and that's where a graph opens upward. So you will see cupping upward, something like that. Concave down means a graph opens downward, so it might spill water if it had water in it. So you could think of spilling water and holding water as a way of helping you remember. In looking at the graph given above, the area where the graph is concave up starts about here. And if you were to draw the tangent lines, just a whole series of tangent lines, where this graph is concave up, you can see that the slopes of the tangent lines would be increasing, because where it started being concave up, the tangents are negative. They're going downhill. At the bottom here, it would be 0, and then we switch back to positive, and they get more and more steep, which is a higher and higher positive slope. Also notice that the tangent lines are below the graph throughout the area where the graph is concave up. Now let's look at the area where the graph is concave down. Starting over on the far left, if we started just drawing a series of tangent lines, you could see that they start very steep and positive, and they get less steep, which means they are getting the slope is getting smaller. At the very top here, the slope would be 0, and then the slopes begin going downward or being negative. So the slopes of the tangent lines are decreasing where the graph is concave down. Also notice that the tangent lines are above the graph throughout the area where the graph is concave down. In section 10.1, we learn how to find where the graph of function f was increasing or decreasing by finding the derivative. To find where the slopes of the tangents, which is the derivative, is increasing or decreasing, we use the second derivative. Another definition is inflection point. This is a point at which the graph changes concavity. To be an inflection point, the value must be in the domain of f. A function f of x is concave up on the intervals where f double prime is positive, and concave down on intervals where f double prime, or the second derivative, is negative. In order to find intervals of concavity, we are going to find where the second derivative is 0 or where the second derivative is not defined, and set up a number line sign chart just like we used on the first derivative when we were finding increasing and decreasing in section 10.1. In our first example, we are going to find where the graph is concave up or concave down and any inflection points. And the first function we're going to do this for is x cubed minus 3x squared plus 1. Now remember, to find concavity, we are going to the second derivative. So we're going to go straight to the second derivative here. The first derivative is 3x squared minus 6x. The second derivative is 6x minus 6. What we're going to do is just like we learned to do for increasing or decreasing. Take that second derivative and set it equal to 0. If you solve that, you're going to get 6 equals 6x, and you get x equals 1. This value that you get that sets the second derivative equal to 0 is a possible inflection point. We won't know until we have done the rest of our work. Just like we did when we were testing first derivatives, we are going to set up a number line, but this time we're using second derivatives. We are going to test numbers on the left and the right of 1. We are going to test them in the second derivative. So let's test 0. If I put 0 into my second derivative, I will get 0 minus 6, which is, remember, all we care about is the sign, negative. So everything to the left of 1 would give you negative answers. Now test something to the right of 1. Let's test 2. We would get 12 minus 6, which is a positive answer. So all the numbers to the right of 1 would give us positive answers. What that tells us then is that we are concave up on the interval from 1 to infinity. We are concave down on the interval from negative infinity to 1. And because we did change concavity at that value of 1, we do have an inflection point at 1. And put this in the original to find the y value, you would get negative 1 as your y value. For our second example, we have the function x to the fourth minus 4x cubed plus 7. Again, we need to go straight to the second derivative. So the first derivative is 4x cubed minus 12x squared, which means that the second derivative will be 12x squared minus 24x. Set this equal to 0. And on this one, notice that we have a 12 and an x in common in both terms. If we pull those out, we would have x minus 2 left over. This means that our zeros occur at 0 from the 12x and at 2 from the x equals 2. So these are the possible inflection points. Sometimes I call them the pips. Take those two values and put them on the number line. Remember, this is where our second derivative equaled 0. And then we are going to test in the second derivative. Let's test negative 1. If I put negative 1 into the second derivative, and I am going to use the factored version of it, I would get negative 12 times negative 3. And what I want to know is, what sign is that? Positive. So all the numbers on the left of 0 would be positive. Pick something between 0 and 2. So let's pick 1. If I put 1 into that factored form, I would get 12 times negative 1, which is a negative. So the items between 0 and 2 are negative. And then let's test 3. Putting 3 into the second derivative, I will get 36 times 1, which will be positive. So the items to the right of 2 are positive. So we now know then that this graph will be concave up, negative infinity to 0, and again from 2 to infinity, it would be concave down 0 to 2. And because we changed concavity, we went from positive to negative at both of those numbers, they are inflection points, both of them. Putting 0 into the original, you will get 7. And putting 2 into the original, you will get negative 8. So those are your inflection points. On example 2, I have a picture that I have given, and we want to state the intervals where various things are true. And question A is, where is the graph concave up? We don't know what these numbers are. They're using letters instead, so we're going to go by x value to x value using the letters. So where is this concave up? Where is it cupping upward? Let's just be very systematic and start from the beginning. As I start from A, I am cupping upward all the way until I get to C. So I want to use that as my first interval where I'm concave up. Then I stay cupping upward from C to D. So that is the second interval where I'm concave up. As we move along, we are concave down from D to E, so we're going to skip that one. Then we are concave up. See how we're cupping upward here? From E to G, so that will be our next interval. And then we start cupping back downward at G. So using what we saw when we were working on part A, we noticed that we were cupping downward or concave down from D to E, and then again from G to H. Questions C and D I put in here just because I want you to recognize that they are asking exactly the same thing as questions A and B. If the second derivative is greater than 0, all that's really saying is concave up. Second derivative less than 0 is saying concave down. So C gets the same intervals as A, and D gets the same intervals as B. Question E asks us to find the x-coordinates of the inflection points and HPI, which stands for horizontal points of inflection. Inflection points, remember, are where you changed concavity. So if we look here, going back up to our first two sets of answers, what letters did we change concavity? Well, if you look at letter D, we were concave up, and then we started going concave down. So D has to be one of the letters where we have an inflection point. At E, we were concave down, and then we started going concave up. So E is also an inflection point. And then the other place is G. We were concave up and then began going concave down. So G is the third inflection point. The other thing that it asks about is HPI, horizontal points of inflection. That we talked about in section 10.1, and what that means is you changed concavity, but you stayed increasing or decreasing. if you look at D, E, and G, if you look at all three of these points, at D, we stay decreasing. At E, we stay decreasing. And at G, we stay increasing. So all of them are HPIs. On example 3, we have a set of graphs given to us, and we are asked to match the graph to the stated conditions. So in looking at the conditions, on A, it says F prime, so that's where we talked about increasing or decreasing. And then it talks about F double prime, which is concave up or concave down. So if F prime is greater than 0, then we want increasing. And F double prime greater than 0 means we want concave up. Which of these graphs is moving upward but would hold water? That is graph 4. Notice that we are moving upward, but it would still hold water. On B, if F prime is greater than 0, we are increasing. F double prime is less than 0, we want concave down. So which one is moving upward but concave down? That is graph 3. You're moving upward, but you would spill water. So B goes with 3. For C, we want decreasing and concave up. Which one is decreasing and concave up? That's graph 2. You're moving downhill, but you could hold water. And then if you look at D, it has to be 1, but what does it talk about? It's decreasing and concave down. Is that what's happening on 1? Yes, it is.